So the last talk in this morning session is on Buckmaster here. So he has done in Leipzig and is now professor at the institute. Circle. Too much to say, so there's no pressure. So the Clay Research Award.
Thank you very much. It's a real pleasure to be here. Wonderful conference. Very thankful to be invited. So in this talk, I don't really want to talk about any specific result. I want to talk about some techniques that I'm using in my research that I think have broader applications. And so I just want to give a flavor of those techniques rather than go into detail about any particular result. So the three techniques that I'm going to describe is using self-solvent analysis, computer-assisted proofs, and neural networks. And so I'm supported by the NSF and the... Oh, that's the... So I just want to advertise to the young people who are collaborators in this work. So Gonzalo Labora, who's a PhD student at MIT, and will be joining me at Quran as a postdoc this next academic year, and Yonji Wang, who's currently a postdoc with me at And so I'll be talking about, so my main interest is the problem of blow-up. So if you take either the incompressible Euler equations or you take Navier-Stokes equations, the problem is, does there exist some smooth initial data that breaks down in finite time? So for the Navier-Stokes, this is the Millennium Prize problem. And so we know in the case for the Euler equations that this happens for non-smooth solutions. But when I say non-smooth, they have some regularity. They're C1 alpha, and this was proved by Tarek Erginti in 2019. And a similar result was proved by Chen and Hao in the case of where you have a spherical boundary, a cylindrical boundary. And very recently, in the breakthrough result, Chen and Hao showed that if you have you can actually have blow up the Euler equations in the case of a cylindrical boundary for smooth initial data. And I'll talk a little bit about that as well. So this is kind of the problems I'm interested in. And of course, the real problem you want to solve is smooth initial data, no boundary, singularity, whether a singularity forms. So I want to illustrate what I mean by self-similar analysis, and the easiest way to show this is just showing a video of exactly what it is. So this is, I'll show in the next slide, this is the, this is the Burger's equation. So it's well known that the Burger's equation has a singularity in finite time. You have a shock, where the gradient, if you look on the top picture, the gradient goes to infinity in finite time. So that's when it stops. So that's the top picture. The blue line, the blue curve, is just the solution to the Burger's equation. And then the question is, what is the picture below? So if you take that red box, which just basically dilates both the amplitude and also the space, and then you stretch that box out such that it makes such that it stays uniform, then the second video is just that red box stretched and dilated. So if you look at the blue line in the second box, it exactly corresponds to the blue line in the top box, but it's stretched in time. And so what you see is that while a singularity forms, the gradient goes to infinity in these new coordinates, stretched coordinates, nothing bad goes wrong at all, actually. It just converges on something very smooth. So this helps. It's much easier to show. So you break that, you turn a problem which is inherently difficult in the sense that you're trying to show that a singularity forms into a problem which is just a stability problem. You're actually trying to prove that things behave well. That's kind of the opposite. So that's what self-similar analysis is. And so to give this a concrete example, so this is the Burger's equation, which is the same thing I showed you in the videos before. I think showing a singularity forms is trivial. You know, you just solve the Burger's equation via characteristics, and you compute the derivative, the gradient along the characteristics, and what you see is that it blows up in finite time depending on the gradient of the initial data. So that's easy. Now, if you want to understand more about that singularity, you can switch to self-similar coordinates, and this is the same image I showed before with the red box. Not working. Anyway, it's the same image I showed before, and so this is the explicit change of coordinates. So this is how you rescale the amplitude, and this is how you rescale the coordinates. So you have this new coordinate y, and you have this new rescaled u, and what you find is that at the time of blow-up, it actually satisfies this equation, which has no time involved. Just a stationary solution to this equation. Of course, you have to figure out what lambda is. Lambda is a self-similar parameter. And so the task then is, instead of showing that the things blow up, you actually just want to show stability in self-similar coordinates. So you want to show that this picture happens, that it converges on this self-similar solution. So the actual singularity is embedded in the singular coordinate change. Okay? So this blows up as t approaches 1. Okay, so let's take this example further. So with Burgers, it's very nice because everything can be explicitly solved, and you have analytic formulas. So in the case of the self-similar equations for the Burgers equation is given here, which I showed you on the last slide, and you have implicit solutions to this equation given here. Now, in order to attack we're not just interested in showing, so there was remember from the first slide, you know, there's results where you show blow up for non-smooth results, but what we're really interested in is showing existence of smooth solutions which blow up. And so what we want is that we want to pick lambda such that this implicit solution is smooth. And you can figure this out. For this to be globally defined, so this is an implicit solution, for this to be globally defined and smooth, you need that 1 plus 1 on lambda is an integer, and 1 plus 1 on lambda is odd. And so you end up with these lambdas. So you have an infinite, there's an infinite sequence of self-similar solutions to the Burgers equation. Of course, there's only actually one that you would observe in real life, because there's only one self-similar blow-up, the shock, which is stable. All the other ones are unstable. So there's only actually one of these that you would actually observe. But as mathematicians, we don't care if we find a singularity that you could never possibly observe. The Millennium Prize has stated, does there exist a singularity? So we're perfectly able to find singularities that are completely unstable. And this will come into play when talking about the Navier-Stokes equation in particular, but even for the Euler. Okay, so you get these infinite discrete set of lambda for which you have smooth solutions. And to give a concrete example, so let's take the stable case where so I equals 1, you have lambda is 1/2. This is the explicit formula for the self-similar solution for the Burgers equation. And this is, up until now, I haven't really explained what I mean by stable. By stable, what I actually mean is that it's stable modulo symmetries of the equation. So, if you modify the initial data slightly, it's not going to blow up at time 1, it's going to blow up at a slightly later time. Or if you translate the data, then it's going to blow up at a different position, and so forth. And if you remove all these symmetries, then being stable means that in self-similar coordinates, the solution will converge to the self-similar solution once you've modded out all the symmetries of the equation. And another way to look at it is that, so you take the linearized operator around the self-similar solution. We're going to add an extra time variable. This is another trick you do. Instead of having the regular time, we switch to this time s, which basically maps. So if the blow-up time is time 1, or in this case it's time capital T, a change of notation, then instead of it happening at time 1, it happens at time infinity. So this is just a trick. And so what you want to show is that it's stable. The solution is stable for all time in this s variable, and that will amount to showing what you want to prove. So if we do this, we end up with this extra s term, and we look at the linear part, and in terms of stability, you can look at the eigenvalues of the linearized operator, and there will be certain eigenvalues which correspond to the symmetries. And if you remove those, the questions are, do there exist positive eigenvalues? And so that's what we mean by being stable. Okay, so that's the first part of the talk. So that's the kind of setup. That's the setup I want to frame everything in. And now I want to give you some ideas of techniques you can use to actually prove. So, I mean, this is so simple because, you have an explicit formula for the self-similar solution, but in general, you have no such explicit formula for what the self-similar solution is. And then how do you go about proving stability and so forth? So the next part of this talk, I want to talk about using computer-assisted proof, and in particular, I want to talk about using interval arithmetic. And this is how you take something, how you can use how you can do rigorous numerics, where you can actually have rigorous bounds and numerics, and how you can use that to actually prove things. And as an example, I'm going to give implosion for compressible fluid, which is a much simpler problem, but it's illustrative of the technique. So let's consider the isentropic spherically symmetric Euler equations, the compressible Euler, and we're going to make the same sort of self-similar ansatz, except it's convenient to add this extra log here in the self-similar coordinates. And so U here is the velocity, rho here is the density, and gamma is the adiabatic exponent. And here, this sigma is a rescaled sound speed. And what's very nice about this setting is that after making these this ansatz of a self-similar ansatz, you end up reducing the equation to an autonomous ODE. Okay, and what's even better is that this is in 2 dimensions, and I can draw a picture. So you have this autonomous ODE, and so all you need to do, well, I'll come to that. So the result of Merle, Raphael, Rodiansky, Zeftel, for which they won the Clay Prize last year, was that for almost every gamma greater than 1, there exists a countably infinite sequence of self-similar solutions, the isentropic Euler, which blow up at the origin. In this case, it's the velocity and the density go to infinity at the origin. Now, this countably infinite sequence, this is very similar to the setting we had before, that we had this countably infinite sequence of self-similar solutions to the Burger's equation. So you'll see patterns that emerge in all of the equations. And it's quite important for their result that they can prove a countably infinite sequence of self-similar solutions. And the reason I'll come to that in a second why it's important. So moreover, what they I should point out that the existence of non-smoothing imploding shockwave solutions, the classical result of Goodley in 1942, but this is a different sort of kind of problem. This is a sort of more mathematical problem where we're interested in smooth initial data, and this probably has more physical relevance in terms of because none of these solutions are stable, so you'd ever actually see them. But we're interested in them just for the same reason we're interested in the Clay Prize problem. So we're interested in showing that there exists smooth initial data that blows up. So let me also, as a sort of companion, as a separate paper, they showed that if you add some viscosity, constant viscosity, then you can also prove singularity formation, in this case for almost every gamma in this range, and for, in this case, mildly decaying density. And the reason why the range is sort of limited is in the sense that you have to have things scale correctly, such that you can treat this Laplacian as an error term. And at the end of the talk, I'll make this very clear of how you can treat this sort of like this second order term as an error. And this is the same principle of the NLS paper. They have another paper where they prove for 6-dimensional NLS, I think, that you have singularity formation. And it's the same fact is that if you, in the right setting, you can kind of scale away the viscosity. And I'll make this very precise at the end of the talk. Okay. So there's kind of 2 questions that are left open. So what they proved is they proved that imploding solutions exist for almost every gamma, but they didn't prove it for any particular gamma. And also, they constructed imploding solutions in the Navier-Stokes equation where the initial density decays at infinity. And what you'd really like to show is that it's constant at infinity. You don't want infinity to play any role in the singularity formation, because it's already well known that if you, say, have compact support in density, it's a very simple result to show that singularity is a form. Or you have rapidly decaying density, it's also very simple to show singularity for the Navier-Stokes equation. The result that they have is not of that type. It's a mildly decaying density, but still, you would not want the density to decay at all. And so this is our result, is that we answer these 2 questions. We show that there exists self-similar imploding solutions for all gamma, and then we restrict ourselves for simplicity to the case that is most physically relevant in terms of corresponds to air. So when diatomic gases, oxygen, hydrogen, nitrogen. And we show that also exists a countably infinite sequence of imploding solutions, which is important for proving asymptotically self-similar imploding solutions for the Navier-Stokes equation with initial density constant at infinity. Now, I'm not going to go into this result. The whole point of this section was actually just to give this as a canvas to show you interval arithmetic. And so that's what I'm going to do. So a key part of constructing these solutions is, if you recall from before, that we reduced to an autonomous ODE. And the nice thing about an autonomous ODE is that you can plot a phase portrait. And this is actually an interesting question, because if it was a higher dimensional problem and we couldn't actually visualize it, it's arguable that it would be very hard to prove it. The fact that we can visualize this phase portrait makes it much easier as mathematicians to figure out a way to actually construct these solutions. So it's very convenient that it ends up being two-dimensional and that we can plot this. So the name of the game is to construct a global solution to the autonomous ODE. And that amounts to connecting 2 points, which is the origin. Remember, this is state space, okay? So the origin is not r equals 0. This is when u, the self-similar u, and the self-similar velocity and the self-similar sound speed is 0. So the aim of the game is to construct a curve which connects the origin to infinity. And that doesn't seem too difficult, except you're not allowed to cross this red line, which makes things problematic. So the red line, obviously, so this is a compactified of phase portrait. The red line, of course, is a barrier from the 2 points. And what is this red line? This red line is just the denominator in the autonomous ODE. So you don't want this quantity being infinity. Now, if you're a little bit more clever, you'd realize that it's okay to cross that red line, but you can only cross that red line when the numerators also vanish. So if you go back to this phase portrait, you have to cross this red line at this point here, where here the green line and the black line are the 2 numerators. So you have to cross at this line. This is the only point you can cross. And so what you want to do is you want to create a curve that goes through here, crosses this line, and goes to this point. And there's actually 2 ways to cross, depending on the corresponding to the eigenvectors of the ODE. There's one way, which is the way that Gooderly crossed. There's one way, which is the way Merle, Raphael, Rodiansky, and Seftel crossed, which is this way. And the reason why you want to actually cross this way is because you can get out here. If you cross like Gooderly did, you'd hit the red line up here. And the reason why Gooderly could cross this line is because he had a shock. So the nice thing about a shock is you can transport from one part of the phase portrait to another part of the phase portrait. And this way you can construct a solution. But when you're looking for smooth solutions, you can't do this. So the question is, when can these points be connected? And a smooth curve that can connect these 2 points can only actually occur for discrete self-similar lambda, and that's the problem. But I'm not going to go into the proof, but one of the main things that you can get from this picture is that it's kind of important to kind of bound where these trajectories go. And so a typical method you would use in dynamical systems to bound where these trajectory goes is you create barrier arguments. You create other curves, and you show that the curve that you're interested in cannot cross those barriers, and that these barriers force it to the position you want. The barriers will force it to go to p infinity and forced to go to p0. So let's consider a completely made up problem. This has no mathematical significance whatsoever. This is completely made up. So let's look at a simple barrier argument. So you have your autonomous ODE, and these are completely made up polynomials. So for the numerators and the denominators, and so this is the corresponding phase portrait for the ODE. And say you have some curve, which is also completely arbitrarily made up, has no significance whatsoever, which is this blue curve here. And you want to know whether this blue curve acts as a barrier. So in particular, you want to show that if any trajectory crosses this blue curve, it can't cross back the other way. That's what a barrier argument is. So you can write this in terms of in terms of the normal to the curve and the ODE, and you end up with this condition here. So you need that this is non-positive for all points on the curve, which is equivalent to if I just multiply everything by d1 and d2, you end up with this this polynomial. Is this polynomial less than or equal to 0? So if I expand this out, I can write this explicitly, and it's a 13th order polynomial condition, which I did not do by hand. Okay, so that's very difficult to show that this is less than 0. But actually, if you just divide by minus t, you end up with a 12th order polynomial, and you're fine. Well, not quite. Okay, so you have this polynomial, 12th order polynomial. And I'm not saying that if you do enough like handwriting that you can art by hand actually show that this is positive. You could, okay? But the real applications are much more complicated than this polynomial. But even this one, okay, this case, so you have this 13th order polynomial and you want to show that it's positive, it's a little bit of effort to actually show that this is positive. Now, if I plot this polynomial, it's obviously positive. Like it's above 0, okay? But again, if you want to, if you want to claim the Merlin prize, you can't just show a picture and say it's obvious that it's positive. You have to prove it. So how do you prove that this polynomial is greater than 0? Okay, so what you do is you'd like to do some numerics because it's the numerics that you trust that my numerics, I mean, I'm not very good at numerics, okay? But you would trust that my numerics are good enough that I can plot a polynomial of 13th order. So let's, what you do is you replace traditional numerics by interval arithmetic. And this is a very simple concept that you can use in many applications, and it shouldn't be scary at all. All you do is that, say you want to, instead of adding two numbers together, you add two intervals together, and you get another interval. And it's not the exact interval. The interval that you can think of this interval as the midpoint plus an error, plus or minus some error. And the error, you always give extra room. So whenever you add or you do any simple arithmetic operation, you always allow for extra room. And you don't need high precision for the error bound. So in this very simple example, what I do is I write all the sort of errors as powers of 2. Okay, so if you do a simple, if you add these two intervals together, you'd get this number plus or minus 2 to the minus 3, and if you multiply these numbers, you get this number here. And so, and the idea is that now you just do your traditional numerics, but you'll end up with the plot of the curve, but you want that the error is not bigger than the distance from 0. So what you do is that, so you calculate, this is just stage code, which is not what we use, but it's just the most easier to show on a slide. So this is the same polynomial we had before. And what you do is that instead of evaluating this polynomial at lots of points, you evaluate this polynomial at intervals. So you evaluate this at intervals and you get error bounds before. And then you should get some result, plus or minus some value, and all you need is that error is smaller than the distance from 0. Okay. So if I do this polynomial and I evaluate this at 10 points, then I get all these numbers, plus or minus some numbers. And what you see here is that the error is the same magnitude as the value itself. And so I can't conclude that some point in this interval will correspond to the polynomial being positive. And same with this point. So we're in trouble, but the easy thing is you just make more points. So you divide up in a finer way, and as long as you divide up in a finer way, you get that the error is smaller than in all cases, is smaller than the actual the evaluated value. And so this is actually what ends up being the case, is that when we do so how does interval arithmetic appear in the mathematical proof? So what you do is that you just do traditional numerics. You check whether what you want to prove is true. So you already know the answer. Okay, and then what you do is you just plug it into interval arithmetic, and you verify that what you already know is true is actually true. And it will sometimes say can't determine, and then you just put it on a bigger cluster of computer. You divide up things more, and then you just brute force keep going with more computations until you prove that it's actually true. So if you like, the interval arithmetic would always be done at the end of a proof. You already know the answer, and you're just using a computer to actually tell you what you already know. Okay. So yeah. So the upshot I want you to take from this is it's not scary at all. It's very simple. Interval arithmetic, and you can use this in lots of settings. So I gave the simplest example. I gave the simplest example where you're checking a polynomial as positive or negative. But you can have much more complicated examples where you take integrals, and you want to bound like differential operators. You can all this sort of stuff is, if you think about it for a second, is not difficult to translate to interval arithmetic. Okay. So when I was in Australia, I was walking down the beach, and I happened to see a mathematician who was drawing on a blackboard and a singularity occurring in the ocean. And so I took a photo of this occurrence. I thought it would be useful. Actually, so this is using generative AI. The only thing that's real in this photo is the blackboard. Turns out AI is very bad at generating images of blackboards with like recognizable mathematics. So if you want to have a sort of barometer of the progress of generative AI for images, ask it to generate a blackboard with mathematical equations. But the rest of it is just AI, and I made sure that the mathematician was facing away because you wouldn't want to see the mathematician's face. And it's good that the hands are kind of very dark, so you can't see the hands, and the shadows are off, and anyway. So this is the last technique I want to talk about is neural networks, and now I want to, so our strategy for proving singularity formation will use all these techniques. And so how do neural networks fit into this role? So first of all, let's consider the case which was recently proven by Chen and Hao, where they consider smooth initial data for the Euler equations outside on the exterior of the cylindrical boundary, which is not true. Actually, they prove it for the interior of the cylindrical boundary. But this is the picture they gave in the original paper, which looks to me as the exterior. And so I prefer the looking at this as the exterior. And actually, the proof is identical, whether it's the interior or the exterior of a cylindrical boundary. It doesn't make any difference. But yeah, just as a slight remark, the actual proof is the interior. Okay, so what they do, so this all started from some numerical scenario in 2014, where they gave compelling evidence for blow-up, which suggested asymptotic self-similar scaling, but at the time they didn't have a self-similar solution. And so what you can see is that as the singularity occurs, so as you have this picture where you zoom in on the singularity, this cylindrical boundary becomes flat. Okay, for the same reason why the Earth seems flat to us observers. And so once you zoom in, there's a bunch of terms that disappear, and what you actually end up with is not the Euler equations, you end up with the 2D Boussinesq equations once you zoom in on the singularity. And so you end up with these equations, the 2D Boussinesq equation. You make a self-similar ansatz, the same as before, which leads to the self-similar equations. And if you can show some sort of nice, smooth solution to this, and by nice I just mean that it's smooth and it doesn't do crazy things at infinity. It doesn't grow too quickly. I should point out that there was some mistaken belief in the fluids literature that self-similar analysis couldn't be used to prove blow-up for these equations. And the reason this was propositioned is that they said that there exists no self-similar solutions which have bounded energy. This was the reason that was given for why you couldn't use self-similar analysis to prove singularity. And this turns out to be very misleading, because while that's true, the statement there is no energy, L2 solution, ones with finite energy, all the dynamics happens at the singularity. And so you don't care about global behavior. And so you can cut it off, and as long as you can prove some sort of stability, then you can actually show that these solutions, as long as they don't grow too quickly in infinity, they can't grow too quickly, that's important. But as long as they don't grow too quickly in infinity, you can prove stability to take these infinite energy solutions, cut them off so they have finite energy, and prove blow up with them. And I think Tarek was one person who kind of dispelled this myth so much. So for a long time, people didn't pursue this strategy because of this sort of false belief that they couldn't use self-similar solutions to prove blow up. Okay, so we end up with these equations here, and if you can prove that there exists some smooth, nice solutions to Boussinesq, and you have some stability properties of it, then you can show that Euler is the same as Business plus some decaying terms. I'll talk about these decaying terms in a later slide. Not for this equation, but for another equation. And then you can prove blow up. And so how do you come up with the self-similar solution? You can't get a nice formula. And so what we did is that we use the physics-informed neural networks to numerically construct these self-similar profiles, and with some equation residue. This is actually a very old image. Okay, so the error here is 10 to the minus 4 or 10 to the minus 5. But nowadays, the error here is basically machine precision. And for anyone familiar with like ML techniques, this is kind of weird because like often for solving PDEs, precision of 10 to the minus 2 is like great. But we have to, if we're going to use interval arithmetic and we actually have to prove rigorous statements, we need the error to be much smaller. And we don't just need the L2 error to be small. We need the high derivative to be incredibly small. And to do that with traditional numerics is actually very difficult. And so in our setting, we can basically get machine precision we can get any order of accuracy for any number of derivatives. Okay, from a practical standpoint, that's not quite true. You're limited to how many derivatives you take. But in any case, we can get far better precision that you could possibly achieve using traditional numerics. Now, how do these neural networks work, and why are they successful? Okay, so everyone's familiar with a traditional Fourier series. And so I should start by saying that this is very different, again, very different than many of the, most of the sort of machine learning techniques that you may have heard of, because in most techniques, what you do is you actually use a traditional numerical scheme to solve the equation, and then you use neural networks to extrapolate that to other initial conditions and so forth. And so your error can't strictly be anything better than the numerical method to begin with, because you're using that to solve the equation. We're not doing that here. What we're doing is that we're representing the solution itself by the neural network. And how you should think about this is that the simplest kind of neural network you could imagine is a Fourier series. Okay, so a Fourier series is just a neural network. It's a one layer, has one hidden layer. This is the hidden layer. And the activation function is sine, and it has no bias. So you can think of like the neural network being like a Fourier series has been a one layer, one hidden layer neural network, and then a fully connected neural network is the same kind of idea, except you likely use a different activation function than sine, except you do all these compositions. So it's just like this is kind of like your Fourier series, and then you apply some nonlinear function, and you already had the nonlinear function here. You take this Fourier series, and then you compose it with another Fourier series, and compose it with another Fourier series, and compose it with another Fourier series. This is what a deep network is. Okay, and why on earth would you want to do this? The main reason you would want to do this is that it can represent, as long as your solution has structure, inherent structure, the neural network can find that structure and represent that solution in an incredibly low dimensional fashion, much lower dimensional fashion than you could with a traditional linear basis. So that in itself is kind of one of the main ingredients that goes into why these neural networks are so effective, is that you can because our solution itself, we're not studying the problem of turbulence. right? Things are not turbulent. The solution is very simple, but it has tremendous amount of structure. So you imagine if you can compress it in the right way, you can represent the solution in an incredibly low-dimensional fashion, and it makes optimization much easier if you can reduce to low dimensions. I mean, this is the heart of numeric analysis, is creating low-dimensional approximations of. So that's basically it. And so what you do, so that's a neural network. I haven't said what you do with it. So let's consider a slightly simpler equation. So the CCF equation, the Cordova-Fontelos equation. So it's like a model for Euler or for Navier-Stokes. Here's your sort of like viscosity term, and it's a fractional Laplacian, so you can look at different alpha, and the question is whether blow-up occurs. You can make a self-similar ansatz, and you end up with this equation here. Okay, but I'm missing a S. I'm missing S is defined in the same way I defined before, is minus the logarithm of 1 minus t. And what you see is that all these terms scale in the same way, but this term scales differently. And so you end up with you don't end up with a stationary equation, you end up with this time-varying equation. And what you want is that this prefactor is negative. And if it's negative, then the viscosity is an error term. It decays. So basically, you want to be in a certain setting where you can disregard the dissipation term. That it decays as you approach the singularity. And so this is the same trick that was used for compressible Navier-Stokes. So we know that blow-up occurs for alpha between 0 and 1/2 by a very simple proof, and we know global well-posedness holds for alpha between greater than 1. So the question is, what happens between 1/2 and 1? Now, in self-similar coordinates, the dissipative term decays exponentially if you have this condition here, alpha times 1 plus lambda is less than 1. And so if you want to prove blow-up, then you need this condition here, that lambda is less than 1 on alpha minus 1. If you want to use the idea here is to use the solution of the inviscid problem, so where this term has disappeared, in order to prove blow-up for the viscous problem. So basically, if you're going back to Euler and Navier-Stokes, is that in this setting, if the scaling is right, then the blow-up of Navier-Stokes is actually just proving blow-up for Euler in a particular scaling regime. Okay, so you end up with this condition, and if you want to say anything about the open range, you need that lambda is less than 1. Now, I don't have much time, so you have your neural network, and how you train the neural network is you plug the neural network into the equations, and you get some error, and that's your residue. You take that, you take the mean square of that, and that's evaluated at certain points, and that's your loss, and you train based on that. You also take the derivatives of these residues and also add that to the loss. And that's how you train. And by taking enough derivatives, you can determine whether the solution is smooth or not, because there'll be a finite number of derivatives you need to actually select the unique lambda where the smooth solution corresponds to. You need some constraints in order to remove the symmetries, and also to make sure that it's not degenerate by having some decay at infinity. And so that's basically the idea. And this is the result. So the first solution you got, which is seen in other literature, is the stable regime. But the stable solution, so this is like in the Burger's equation, I thought that there was different lambdas. And the stable one has lambda 1.181, and so it's not useful at all to prove this open range. But if you take the next solution, which is an unstable solution with this unstable eigenvalue 0.367, not corresponding to symmetries, then the lambda is 0.606, which means that you can actually start attacking this open problem. And maybe you can come up with a conjecture that if you could find an infinite sequence of solutions like you could in the compressor auto case, maybe you can attack the full range. That's possible. But of course, you couldn't pursue this because you can't numerically you can't construct an infinite number of solutions. You can get arbitrarily close. This slide is broken. What I wanted to show is like what the training kind of looks like, and I just wanted to show like at the early start of training where it's very noisy. And so this is the U, and what you can kind of see is it learns certain features at different steps. I wanted to just show it's not some smooth convergence. There's like little jumps as you go, and the same with there's a bit of stochasticity involved in the residue. But yeah, as I said, this is broken. There should have been an omega here, and I don't know why.
So you numbers were sort of understandable. So fact
Yes. Yes.
and where biggest I mean is the biggest complication then neural net coming from there?
Okay, so yeah, I don't have any results to present which show the whole program, and we should have something soon in the summer representing like the CCF example, which shows the whole program start to finish. So you end up with a numerical solution, and then to actually prove stability of that numerical solution is not simple, I would say. And one of the reasons why it's not simple is that it's not just about eigenvalues, because it's if you had a symmetric linear operator, then you could deal with the eigenvalues, but this is not symmetric at all. And so you need much more intricate bounds in order to close everything. And so, as an analyst, I'm very used to putting a tilde underneath than less than equal. Like I don't care about constants, and it's very difficult for me in this setting. Is I cannot do that. At every step, I have to say what the constant is, and you need to keep track of these constants and make sure in a nice way that like we have a setting where basically all the errors go to zero. But the question is how quickly do they go to zero? That I can actually run it on a big computer and have it done. Because if I end up having to do things with matrices that are 1,000,000 by 1,000,000, that's expensive. And so you want that the convergence is very fast in like I didn't say the last thing is that you take this neural network, and once you have that neural network solution, you throw it away. You just take that solution and you represent it in a linear basis. So it's kind of the opposite of what I was saying before. And the reason you do that in a linear basis is it's much easier to prove things in a linear basis than it is that. So once you have that neural network, you throw it away, you represent it in a linear basis, and then you prove all your bounds in that linear basis. Now, getting an entire scheme of that working is a lot of work. So that's one thing. But we more or less have that. From the neural network's point of view, it's harder and harder. Like the more unstable the solution, the harder it is to find. Like the neural network doesn't, it has the advantage that so a traditional way that you construct these self-similar solutions is you evolve things in time, and this works if the solution is stable, because if it's stable, it will converge. But for all the solutions we're really interested in, none of them are stable. So you cannot use this technique. Now, neural networks don't, this approach doesn't have that problem. Having said that, in order to determine whether a solution is smooth or not, if you actually go back to the burgers example, if you take lambda to be very small, for very small lambda, the solutions will be very regular. They'll have lots of derivatives. They won't be smooth, but you only see that at the 10th derivative level or the 12th derivative level. So the higher the instability, the more we have to be able to keep track of the higher the higher derivatives of the residue. And so this becomes increasingly complex. And so for Euler without boundary, or for similar equations, like finding that unique lambda is a difficult task. But in general, there's progress.
So, but still, I mean, just for the computer analysis. So we resume at 2:30.